Let's start. So this is the part of the course, which is like the third and the last module of the course where we are talking about game dynamics. So people are playing a game, and the question is, how should they meaningfully engage in the game so that a desirable outcome is attained? Okay. So a desirable outcome we have seen can take on many different forms. Like what is the desired outcome, that depends on whose objective we are looking at, and so on and so forth. So suppose our desired outcome was reaching an equilibrium. Why? Just a brief recap, because equilibriums are this sort of steady state of a game where no agent, or even in sometimes groups of agents, also realize that there's nothing they can do to strictly improve their outcome, right? So for the moment, for this particular part, let's assume that equilibrium is a desirable state that we have to attain, right? So the question is, for any arbitrary game, can we always say that such an equilibrium should be attained? Right? Yeah, it's not clear. The question is, what kind can we design games? Okay, so for the purpose of this, we will talk about pure Nash equilibrium, pure strategy Nash equilibrium. Okay. Yeah, but for more generalized game, one can, but we'll see mixed strategy Nash equilibriums are a bizarre sort of objects. We are talking about sort of an gain in improvement expectation. It's a sort of a couple, it's a coupling of a bunch of different strategies and so on and so forth. So for the purpose of this thing, we'll talk about pure Nash equilibrium only. Okay. So the first question is, and I write here the word, do strategic agents. Strategic agent means people who want to maximize their own outcome. They don't really care about other people's outcome or the general welfare, the robustness of the game or the overall other thing. They are only interested in their outcome. That's what a strategic agent means. So the question is, can they do strategic agents reach equilibrium? In this case, a PNE, a pure strategy Nash equilibrium. If they do reach, if the game has the property that it can reach, the question is how fast, right? In particular, you would see if the way the game is proceeding, if the game rules and the configurations of the game allow, where people sort of get caught in a loop and a cyclical this thing, there's no end to the game, right? The game itself won't end. There's no reason to believe that why should anything change? Literally, the meaning of a cycle is that you're caught in it. And so the question is there a sort of path through the game possibilities configuration so that the equilibrium is reached? Okay. Think of it as like a graph traversal, where the vertices of the graph are these strategy profiles. Somebody does something else, you move to another vertex. From there, somebody else does something, you move to another vertex. Okay, so the transition, the edges represent transition from one strategy to another. Okay. So in this case, if such a pure strategy Nash equilibria exists, in this particular game thing, we can imagine the source is like whatever the initial strategy is. Let's say there could be multiple source. We can create one artificial source and say everything sort of, that's the unique source. The sinks of the game are the pure strategy Nash equilibria, right? Where the idea is nobody has any reason to deviate because they are not going to get a strictly better outcome. Okay, so as long as there is even one agent who can have a strict improvement, there is a transition edge from which you can leave a vertex. A sink is one where there are no outgoing edges. Okay, so this is think of this sort of a strategy graph, profile graph. So a path to a series of steps that reaches a pure strategy Nash equilibrium would be a path from the source to a sink. Yes, that's a question. If a sink does not exist, in this particular description of a graph, there is no pure strategy Nash equilibrium. Yes, all those are meaningful questions. That's why I wrote, can they reach? The point of can they reach really means, first and foremost, such a thing, object even exists, right? Because we have seen ample games where there is no pure strategy Nash equilibrium. But we have seen some a category of games where pure strategy Nash equilibrium always exists. Do you all recall? Okay. Pure strategy Nash equilibrium. That you're thinking about dominant strategy equilibrium. Okay. That's not the point. I'm saying class of games. Actually, pure Prisoner's Dilemma has it, but potential games. The last several weeks, that's what we have been talking about, right? Last week you saw, not last week, 2 weeks ago, you saw cost sharing games. Before that, I talked about those atomic selfish routing games and so on and so forth, right? Selfish routing game. The category of those, or there's this thing called location games. I don't think I said much about it. So these are all category of games that fall into this thing called potential games. They have a pure strategy Nash equilibrium. In particular, the strategy that minimizes that potential function. These games have a very nice description by which the description is that there is a potential function we can associate with the game which tracks the unilateral deviation of the players. Now, not all games are amenable to this type of analysis, but those that are minimizing that potential function, finding a value for which the potential function attains a minimum value, gives a pure strategy Nash equilibrium. That was from several weeks ago now. So there are games in which such a thing can happen. Like at least a pure strategy Nash equilibria exists. Now the question is, will the agents find it? Right? By just doing this sort of. So there's a path from the source to one of the sinks. I say one of the things because they might be multiple different the pure strategy PNEs. So the source to path, source to sink, and what is the length of the path, right? If this path, there is a path, but in between there is some type of a cycle. If they get caught in this loop, they may never reach it. Okay, so this is the sort of thing that we are talking about. And yeah, so that basically is this question: how, when, and how will it happen? Can we guarantee this? Okay, so a PNE exists, but it is not. Okay, yes, it could happen. And okay, when could that happen? So the graph I described is one. So I gave a very scratchy description of what this transition is. The transition was just basically taking you from one strategic profile to another, right? We'll talk more precisely about what this precise kind of transition function is. But yes, supposing you have a source and there exists. So basically, this graph consists of all possible strategy profiles. If you can move from one to another, with whatever the game allow. In this case, suppose we are looking at Nash equilibrium. We are looking at Nash equilibrium. So we are only talking about unilateral deviation. So one player is changing its strategy and others remaining the same. So when I say unilateral deviation, it means that you have a strict improvement. That player has a strict improvement. People don't just change just to remain the same, or definitely will not do to go down. That's what strategic strategic behavior actually means. It's a strict improvement. Okay. So if there exists it's possible that there exists a strategy which is a PNE, pure strategy Nash equilibria, but players will never be able to find it by a sequence of deviation, sequence of unilateral deviation. Yes, that is possible. In essence, it's possible. Okay. Yeah. So all of those things are what we are talking about here. That's what the whole subject of game dynamics does. Okay. Here, if you think of it from the player's perspective, we are all in this. Suppose the game goes on for, in sets of several steps long and so on. I'm thinking about what to do so that I get a strictly better outcome. Other players are also doing. So in this sort of multi-dimensional thinking space that we are inhabiting, where we all want to strictly improve our sort of gain, question is, can we somehow weirdly, all of us approach that PNE. Okay. Yes, then maybe the previous one's value goes down. Then the question is there another strategy that the previous one can play that will again lead to a strict improvement? Then there will be another edge leaving that vertex. That's the literal point. PNE is that vertex where there are no edges going out because nobody can strictly improve by a unilateral deviation. That is the point. Okay. Now, so this is a class of this is the type of game theory that has been studied for a long time. It's not new. It's a classical topic. That's why we are even talking about it. But you understand that these things have taken on a new meaning and sort of emphasis given the world that we are living in, and everybody is trying to study, learning theory, machine, because learning algorithms are very much the need of the hour, right? So essentially, these are learning algorithms where the learning part is learning the game, how it's proceeding, like how others are logically think, how others are behaving, how others should behave, etc., etc. Okay. Now, one thing to note here is this that given any so just one other point. So the reason why potential function analysis works, and it is descriptive as well as prescriptive in the sense that the solution it gives captures the quantity we want to study, PNE, is in part because the potential function captures this sort of behavior where anytime somebody has a unilateral deviation, the potential function changes, and the change can be sort of, it falls. So there will be a minimizing value, and it captures the idea that all of us, even though we are trying to maximize our own individual gains, we are somehow together moving in the same direction in trying to minimize this function. That's the sort of idea. Okay. This is why. So this intuition is something keep in mind. We'll see sort of why that becomes useful here. So going back to this thing about games and learning in games, one can agree that for any game, the way I am learning the game, the type of strategy I am using may be very different from yours, from another person, right? All these things. So it's very hard to say this game will evolve. It's almost impossible to say that this particular game will evolve. The learning dynamics will be exactly like this. There are many different ways to play the game and therefore to learn also. Okay. However, so what are we trying to do here? What we want to say is we want to get some guarantees that are like use very simple ways of logically thinking about the game. Almost a condition that it seems like this is a necessary condition that every agent should try to attain step by step. Okay. And we want to be able to attain a guarantee which is robust against many different ways of thinking about, as many ways as it is to think about it. So, in a sense, it's like saying, even though I have no particular way of knowing that exactly if this is going to be the dynamic source, this is this, but still the results sort of capture a general class of behavior, general class of reasonable behavior. Okay, so this is the thing. So I don't want you to think that this is the only way, because I'll discuss that there can be other ways of thinking, but still the guarantees we will see today somehow hold across many variations. Okay, all right. So in particular, today we will talk about this thing called best response dynamics. Okay, so it's the most sort of the conceptually the most simplest thing. Here is a strategy. All of us are thinking, does any one of us have a unilateral deviation that will lead to strict improvement? Okay, that's what is called. So in some textbooks, some papers, this is going to be called better response. It's like, this is the situation we are in. This, if I change my strategy, just mine, while others remain the same, this is going to be a better outcome. So I move there. Some books will use best response because, yeah, we'll see why best. But this just thing where we transition from one vertex to another, just the fact because one of the agents has a strict improvement is what is called a better response or best response dynamics. Sorry? Yeah, no, strategy, just strategy profile. Like I'm playing strategy. We are talking about pure Nash equilibrium, right? So I'm playing action one, you're playing action three, he's playing action four, and so on. This entire configuration vector, which precisely says which agent is playing which action. Okay, that's what a strategy is. These edges are this. Sorry, this is the source. This edge basically means if this just one agent is changing, A1, he's improving, and that takes us to this new strategy where everybody else remains exactly the same as they were in the source, except for A1 who has changed. From that point onwards, it could be, you can imagine, there can be now maybe it is A3 did not have a strict improvement from here, but now from here, A3 sees, okay, I have a strict improvement. So it takes you to this thing. From here, it might be some other agent says, okay, no, I was much better over there. But like this is this thing. So this guy comes back here. So this could very well be A1. Okay, so you can label these edges. Sorry. You're right. Yeah, okay. This directions don't actually make sense. I just randomly drew some, you're right. So here is the point. Okay. What this was representing is, see, this is sort of it is a vector, of course, but you can also sort of represent it. So whatever this was representing, it was representing a possibility where only A1 has changed from here. Whatever A1 was doing is an action maybe available to another player also. Okay. So no, this edge does not make sense actually, but this thing makes sense. A2, yeah, then A1. Okay, A3 also. Yeah. So see, this is the thing. So an agent could have multiple deviation strategy. If he takes this strategy, he goes into this vector, to this strategy profile. If he takes another strategy, he ends up here, and so on and so forth. And this is the sink in this thing. So such an object, basically this means that nobody has an outgoing edge, no air, meaning no agent has an unilateral deviation. This is why this is a sink, and by definition this is also a PNE. Okay, so this is this thing. Okay, so the basic heuristic, yes, sorry, no, it does not have to be a DAG. You can have bizarre situations. It actually does not. I have a much more better figure here, which, yes, does not have to be a DAG at all. Yeah, sorry. This is the strategy. This is a strategy. Vertices here are strategy profiles. The, yes, yes. That's what I was trying to. Yes, you can have multi-edges. Absolutely. Wait, let me just maybe draw it quickly. There is a much better. You can see all this. This is. This is exactly the point. This is, say, I1. This is, okay, let's just say I6. This is I3. S4. Something. Yeah. Yes, of course. Okay, of course. So from S1, there exists a transition by which I1 strictly improves and they end up at S3. There can also be a transition from S1, which actually gives an improvement to agent 6. And they both situations lead to ending up at S3. Okay. So this is the thing. Okay. This sort of thing can happen. To answer your question, see, this is the cycle. This is low meaning. Yeah, of course. Between this sort of cycling back can very well happen. But I'm saying you can also have this sort of thing. People did this and then suddenly, weirdly, you're back. How are two cycles possible? This sort of a cycle, this is a two-length cycle. Yeah, because this is a labeling. This is what was this thing. I mean, these labels as such, he didn't describe any particular, uh, it would take a huge amount of description to say, but this can happen. You were here. I2, agent 2 has a deviation. He ends up in S4. But that S4, I5 has a deviation that takes them back to a strategy S4, this sort of thing. There is something else I2 can do, right? Sorry, repeat your question again. You're talking about specifically this guy? Okay. Yes. So this is just saying that S1 is not a PNE because there exists agent 2 has a strict unilateral deviation, meaning that will give a strict improvement. That deviation will take the whole game to S4. From S4 also, there exists a unilateral deviation, but this time for I5. And if we go there, we are back to S1. So I2 is not changing. In S4 is basically perturbing whatever S1 was, but just I2 doing something different. Okay, that's it. S4 would be basically whatever S1 is minus, let's say, I2. This notation you remember? And something, I don't know what I2 is doing here. This is S4. From S4, see over here is this portion where 5 was not doing anything, right? 5 was doing whatever whatever S1 was. Now here, agent 5 realizes I am playing something within this thing, which is the same as what I was doing S1. Let me do something else. That will give me a strict improvement. Okay, so you are possibly thinking that SI2, and these are things like, this is in terms of like a vector. So I guess what you're thinking is that, okay, if agent I2 is doing something in S4 and he continues to do this, how can agent 5's behavior take him back to S1? The whole thing, that's what you're saying, right? Okay. Imagine an example where it is basically like choosing a path in some type of again, here's also a path. So this strategy profiles, these are not exactly precisely the way we talked about strategy profiles in the first part of the course, where we are literally saying, I'm playing paper, you are playing scissor, somebody else is playing rock. And therefore, if I just change from what did I say? I played scissor, right? If I change to paper, you still continue to play whatever you were. How am I going back? So it's not this strategy does not quite encode that type of thing. All we are saying is I change to scissor from rock, let's say. Okay, let's just write this, okay? Scissor, rock, paper. So who kills scissor? Rock, right? Rock kills scissor, no? Yeah. So then I realized, okay, I don't want to be do this. I will change this to paper, rock, paper. Okay. You realize that no, I'm going to now change to rock, scissor. This sort of a thing. Okay. So ultimately, what is happening is, but did I give a proper example? So I end up being paper. This is not a good example. Scissor. I change. Okay, let me say I change to paper because I don't want to be changed to. Okay, let's play with two people. Yeah, wait. I should be able to work out this. Just 1 second. Okay. So I see scissor. I change to paper. Okay. Okay. Now this person changes to what is it? Scissor. It's not the same thing, but okay. So let's see. But am I not? Okay. But for me, I end up being killed, right? Like this was a losing strategy for me. I was playing scissor. I was losing. I change here to paper. Temporarily, that was a relief. But this guy also changed. So I end up being losing. That sort of a thing. So the node just represents the fact that here is a configuration of the game. And using that, we are able to infer what would be the payoff for all the individual player. And the players can also do it. That property is necessary so that they can evaluate what is, if there exists a deviation for them. Do you have a better example? Yeah. Yeah. Say again. Bodyguard problem to. Okay. Yeah. That is a better this thing. Yeah. So if you transition from here to here, this person can switch from here to this. That sort of a thing. But it's called a bodyguard problem. Huh? Okay, so this sort of it's a oversimplification of this, but you can let me think of a precise game where this sort of a transition happens. Um, yeah, yes. So you are assuming, okay, I should have, you are assuming this is this thing, right? Yes, this is the classical notion of a strategy. Here, however, imagine a game which is sort of, if the best way I can think of this is to actually talk about traffic type of situation. So I am playing exactly, I'm using the same road. Suddenly, lot of people join my road because they think it is better for them than wherever they were. I did not change my thing, but the cost I am incurring is worse because these other people have joined me. There's more traffic on the path I was traveling in. Okay, wait. Now, initially, the reason I'm even in this traffic, in this path, maybe because I moved from some other path. So I have not changed back to the old path. But all these people joining in have caused the load in my current path to be as if I was in the older path. A group of people are? Yes. So this is where we will actually see that we will think of this as a atomic routing game, where there are n agents, but their identities don't actually matter. What matters is what they have committed to play. This is why somehow in this reason, I guess, this is why these are not potential game. The best example I can think of is a road network. Like I did not change I was here on this path. I realized I should take this bifurcation. Load will be less, so I'm traveling there. Somebody else moved from their path and I have now joined my path. So I've remained in the same thing, but the load on my path has increased so much. So to me, my utility, my travel time is back to what it was before. That's the sort of thing these kinds of transition represent. I don't think there's any way of explaining this sort of thing by these sorts of games, basically. Okay. All right. So let's just move on. So this, do you understand what this is happening? So as long, this is exactly the pseudocode representation of what I just now said. That as long as there is something to do, as long as we have not reached a sink, it means somebody has a transition edge that they can take. So they move to this. Okay. Can you analyze this game? Like, can you say what can happen if we did something like this? It's important to say arbitrary agent I. As long as there's no outcome, pick up a unilateral strategy okay, and move to this. Suppose there are two agents. Each one has what? Okay, not two agents. Let's say K agents. And they have two strategies each. Okay. So this itself could be 2 power K possibilities, right? Among themselves. The fact that we are picking any arbitrary agent I and allowing even a smallest of small incentive to sway us means even if we were doing this potential function minimization business, right? The improvement per steps could be very, very small. And therefore, the total time of convergence could be very high. Sorry? Yes. So if each step improvement is so infinitesimally small, the convergence time basically effectively becomes possibly infinite. Right? So what do you think is a simple enough fix to avoid this sort of situation? One, you say? You maximize, like if there are several deviation, choose the one that gives you biggest jump. Okay, is that the only thing? You have something else to say? Not? Okay, if that is the case, we would be at PO. And so if I could guarantee that my improvement will not adversely affect the other people, that's a much harder, like, you see? Yeah. Pair to optimality. I'll get to this thing. Okay, he knows, so that's why I said. Yes. Say. Yes, that's a natural thing. It's like a threshold. The improvement should cross some threshold. Otherwise, I'm not moving. So if this is the case, if each time I am ensuring, so let's go back to this picture of the potential function thing. Suppose we are actually trying, the PNE is captured by minimizing that potential function. We'll make that formal. So the point is, how fast is the potential function moving? There's a minimum value. Question is how fast it is moving. If each time the potential function drops, it drops by a chunk. The number of steps that would require it to reach its minimum should be smaller, depending on how large that chunk is, right? There's a natural trade-off, right? It's like a finite amount of distance I have to cover. Each step I'm taking, epsilon, epsilon chunk. The question is, the number of steps I might have to take would be shorter. That's the general idea, okay? So you said we will take the best possible deviation possible from this thing, right? Okay. So that is where the name best response sort of comes in. Okay. Now the question is, how do I capture what is best response? Okay. I write hyphenated because I'm sort of associating. Think. So should it be the difference like subtraction? Should it be the ratio? What should it be? Turns out all these are good sort of ways of thinking about this. Okay. And we'll prove a result which is somewhat robust across all these sorts of things. But we agree that we should at least say the improvement should be guaranteed by some value. So he was saying the improvement should be at least like some some epsilon fraction and so on. Okay. All right. So let me, okay, tell me, remind me what's a potential function or potential game. Potential game is there exists a function such that what? Hmm? I'll just write the, let's say like this. We'll use it. I hope you remember this notation. This is just agent I switching. So this describes a unilateral deviation. This is equal to agent I's this is the original. Okay. So, okay, this is a notational. It's a weird thing. Wait, it's a bit of a, what I want to change, say is change in cost for I. Okay. So let's write it this way only. This is what this is supposed to track. Let's write it this way. I'll use it. Yes, tell me. This is a definition and I'll say more. Yeah, tell me. Yes, that a potential game is one where there exists a function such that for all strategy profile, for all strategies available to this thing, agent I, this happens, right? Okay. Now, this is all just to recall, okay? Wait, I wanted to say some other. Okay. So the setting here is the following. Let me write all this. I don't want to delete it. An atomic selfish routing game. K is the number of agents. Single source single destination or target. So in the variation that we studied, we allowed the K agents to have different source, different destination. In this case, we are assuming them to be the same. Okay. This can be easily done, add an artificial source, artificial sink, and so on and so forth. Now, I'm going to say, okay, CI is the cost function for agent I. Okay. The theorem we will show is the following. Yes, please continue. You can do this. Yes. So the whatever this is, if single source is sending R, you. Oh, so if you remember in the atomic selfish routing games, we said every agent is in control of one unit of flow. Okay, so those things are implicit here. Okay, so you have K agents, each one is sending, controlling one unit of flow. Okay, this thing, what this does, but this is an important point here. The point is the paths available to an agent one, in that case, was a P1, set P1. These are all the S1, T1 paths, right? Here, then the S2 to T2 paths were the strategies available to agent two, blah, blah, blah. In this case, the portion, the part that we are assuming that suppose all paths are available to everybody, and it's sort of a single source, single destination sort of thing. So that is not exactly the same thing as saying this, because here there is a the point is, this sort of hedges the fact that agent one has to go from S1 to T1. He does not want to end up at T2, first and foremost. And if the artificial sink and source sort of thing says that, okay, all these people have to do is go from S to T. And it does not necessarily say that agent one to leave source S, he only has to go via S1 and so on. That can be done by saying that agent 1, agent 2, agent 3, and other people's cost of traveling this edge is exorbitantly high. Those sort of thing can be done. Okay. So, and therefore, only agent 1 will want to go from S to S1. Everybody will basically leave the artificial source via their correct original source. Okay. So all these things can be done. But so let's assume that we have a single source, single this thing. In a potential game, I just want to say this. Let's be here. From any arbitrary initial outcome, best response dynamics converges to, it's called convergence. Okay. They don't somehow, it's for historical region, they don't reach, they say convergence, just to a PNA. Okay. So can we prove this just in one line? The potential game has a potential function phi, right? There exists phi corresponding to the game. Right? So from phi to phi min, what can we say? Yes. So this, we are saying nothing about the number of steps taken to converge. Just that from phi to phi min, there exists a way of reaching, right? And that is given by the analysis of the potential game that we saw before, right? So is PNA. So this is basically the argument. So from, in other words, I should just say that dynamics tracks movement of phi wherever you start from to whatever phi min is. Phi min is the sort of the state at which this quantity is minimized. Phi is minimized. Yes. You were saying something? The possibility for every player is finite. Say that again. Okay. Yes. Yes. Correct. So that is basically was the essence of the proof that the potential function minimization happens. Right? That's basically the idea. That was basically the point. So over here, I just use the fact that we know this minimization is PNA. That's the idea, right? Okay. So now, so we know this happens.
Hello.
The question is, somebody said something?
Yeah, could you please pan the camera to the right? I'm not seeing the board.
Okay. All right. Okay. Now let's just. Okay. Now we will talk about an epsilon improvement. Okay.
Thank you.
I'm going to write here I has epsilon. I'll say what epsilon improvement is. Okay. Okay, maybe I should first write what. Let me just delete this. Okay. So this, you know, this proof. So I just want to use. So let's define what it means to be epsilon pure Nash equilibria and the corresponding notion of epsilon improvement. What do you think should be the definition of epsilon PNA? It's a fabricated definition to basically use this idea. I will only shift if I have an epsilon level of improvement. So if I'm not epsilon improving, if nobody is epsilon improving, then I declare it to be an epsilon PNA. That's the idea. Okay. All right. So let me just write it though. I need this for every this thing. Outcome S of cost minimization game. Okay, this is the same as epsilon PNE. If for all agent, all the cost of agent I. By the way, this is important to say cost minimization game because you remember in the atomic routing games, our payoff was not a maximizing quantity, it was minimizing. Payoff was travel time. So it's not the other kind of game that we saw where we are trying to maximize our payoff. Here we are trying to minimize our cost. Okay. So that's why this is important to say cost minimization game, because otherwise this whole thing will not make sense. Okay. So what do you think this should be? Less than equal to the improvement, the reduction in cost should be what? Whatever the agent was before. Correct? Sorry. So we say something originally at the very start of this thing, we were saying a unilateral deviation makes sense when somebody's payoff is strictly improved. Over there, the word payoff means something you're trying to maximize your valuation or utility function. In traffic games, routing games, our payoff is computed in terms of travel time. Travel time is an object that we want to minimize. So therefore, the terminology has to adjust itself. This is why we write cost minimization games, okay? So when we are saying cost minimization, what does this mean? This is the cost agent I gets after deviation. It is at least in other words, that no agent has an epsilon deviation strategy. If this was flipped, it would mean the agent's value falls, right? After deviation falls by this much amount. That incentivizes him to unilaterally change. Okay, so this is the thing. Okay, so what was I going to say before? All right. Okay, so here, let's say that is no player has an epsilon improvement. Okay. I has, so when we say I has epsilon improvement, it means anything more than epsilon could also be. Okay, one such epsilon improvement, then the update would be improvement S prime I. Then you change, otherwise you don't change. Okay. All right. So now, what kind of guarantees can we get? Do you think this is good enough, or should we tighten it a little bit more? I'm going to take it a little bit. So yeah, so all I'm saying is, can you tell me how to extract a guarantee now of convergence, rate of convergence? So somebody said, so let's do this hybrid approach. Not only we want epsilon amount of improvement, but let's allow only that agent to change who has the highest possible improvement. There can be multiple agents who see epsilon improvement, right? We change according to the deviation which gives biggest improvement. Okay, so biggest improvement what means what? Biggest reduction in cost. Okay, so with that variation in mind, I can yeah. Sorry, say that again. If I why do you say that? I don't, at a time, I don't really know how far I am from an P and E, right? So I'm not actually saying that. Here, all I'm saying is I look at a current situation. I'm just saying, is there something I can do that will give me a strict improvement by a factor of epsilon? The strategy that I end up adopting may be very far from PNE, the actual epsilon PNE. Epsilon PNE means nobody has an epsilon improvement. Nothing. This is just a definition that basically, so we define epsilon PNE. So we wanted to talk about the actual PNE, but we saw by this sort of a thing, if I improve with the tiniest possible this thing, which is not prevented by this, I mean, the point of converge potential function has a PNE. Question is how far I'm reaching. Okay, so we have answered this question for potential games, right? From what we have seen before. So now this is the question we are answering. And so then we are adopting what he suggested, which is that we will only change in chunks when the improvement is in chunks. That says that the potential function is moving fast enough, step by step. So to capture that essence, we define this notion of epsilon improvement, or rather the sort of associated notion of epsilon PNE. That's what this is. Or in order to apply this definition, I am not saying anything. So this S is an epsilon PNE if no agent has a unilateral deviation that gives him a improvement by a factor of epsilon, right? This is analogous to our original definition of PNE, that no agent has a unilateral deviation that gives them a strict improvement, right? So here we are saying strict improvement by a factor of epsilon. That's the only thing. And over this, we are going to we change this into epsilon best response dynamic by saying that just don't pick an arbitrary agent I with some unilateral deviation strategy. Pick an agent I who has an epsilon improvement. Just so that I can move the potential function faster along. This is a potential function, right? By definition of epsilon improvement, it means this will fall by a factor of epsilon. 1 minus, this will, how each step by step, this improvement will be what? Epsilon. 1 minus epsilon, right? Yeah, right? So that's the thing. So is it clear what I'm trying to do here? Okay, so now there is another variant of this, which is called epsilon response max gain. Okay, what do you think this is? It's basically what I was saying, that don't just pick any I, which has an epsilon improvement. See, these are very heuristical in nature, right? These are almost, these are almost common sense, greedy type approaches, right? So pick agent I, pick I, who does what? Arg max Ci minus Ci okay. This one was known before. This one was this. So I can basically take this out and write it this way. Okay. So pick I that maximum. This difference basically captures the largest improvement. Yes, largest fall in cost. Okay. When I say improvement, you have to think about condition specific. Sometimes improvement means improvement in value. Sometimes it means reduction in cost. Here we are talking about reduction in cost. Okay, all right. Okay. That maximizes everything else remains the same. This sort of update, huh? Okay. So now we will show this theorem. Okay, we'll work there. Theorem 1, I'm going to write, consider atomic selfish. Let me write the conditions and then I will explain what they are. All agents have common origin and destination. Here, notice something. For alpha greater than 1, cost function. So remember, in atomic selfish routing games, we had cost function associated with every edge. And the cost function had certain sort of reasonable property, right? Cost function CE, it is again this thing. It's a real value, this, such that satisfies this property. CE x plus, I'll explain what this is. It falls alpha x for all. Let me write it this way, okay? Okay, sorry. I will write positive integer. Tell me why. I first wrote real positive reals, but then I changed to positive integers. Atomic selfish routing, you don't fractionally deviate. The version that we studied, we don't fractionally split the cost. Every agent decides to send its one unit of flow across some path. It can't be like, it's not like I have 1 unit, I send 0.5 through this, 0.5 through another thing, and so on. That's the thing that was allowed to do in non-atomic selfish routing network. So just 1 second. So when we capture, so recall, this quantity in atomic routing denotes the number of agents that are using path that contain E. Okay? Yes, you were saying something? Okay? So this is something to keep in mind. So literally, so what does this, it is called the alpha jump condition. So as you, with every additional agent who uses this edge, either the cost remains the same as before, okay? So this is like those fixed cost paths that we had, or it increases by a factor of alpha. So tell me what all class of cost functions this prevents. No, I'm not asking in that way. I don't know how to analyze submodule, at least in this sort of a way. All I'm saying is, notice you're not prevented from sort of having, uh, yes. So with every additional person that uses this edge, the increase in cost is by a factor of at most alpha. It could remain the same because this is a range, right? It could remain the same, or it at most increases by alpha. Okay. So what you're not allowed in this thing is to have this sort of weird network where beyond a certain value, more load passes and somehow telekinetically you are sort of being transported. Okay. That sort of thing. This does not preclude this constant value edges. Okay. All right. Now, and then then the max gain variant, epsilon best response dynamic, okay, converges to epsilon PNE in how many steps? Can you tell me? Like, take something that you seem is close to ballpark. I'd be very happy if you can tell me something that captures the essence of our discussion. Okay, let me write it here. Ln 0 min. Okay, where S0 is the initial state, phi min is the potential minimizer, minimum value, minimum phi value. K is number of agents and all these things, and so on. Does this seem at least somewhat reasonable? Of course, we'll see the proof, but I'm saying, why does this seem reasonable, if at all? Wait, John? As epsilon becomes smaller and smaller, it should, 1 by epsilon should grow. So yeah, naturally, it should be inversely proportional to what the epsilon's behavior is, the number of steps. Good. What does this thing represent? Right. Correct? So it's if, think about epsilon phi of S0 as the starting point. The distance traveled, like the entire value traveled, the value has to go all the way to phi min. Each step that we are doing, our idea is the phi moves by an epsilon fraction. Smaller the epsilon, smaller is the movement, right? Bigger the epsilon, bigger is the chunk. But how many chunks, how many steps it is, if it is correct that I move, if I could think about this entire distance from phi 0, let me just write here. So this is a general, you have seen this calculation type of idea elsewhere. It just is used in a slightly different flavor here. So think about phi of S0, phi of min here. If I can, this entire distance, if I can break into chunks where the improvement is by a constant factor, constant fall. How many such falls can there be? How many such blocks can there be? Think about if each time you take half out of phi S0, another half, and so on, right? It would be natural base, it will be log base 2 of this difference between phi S0 and this. Okay. So now, if the jump is by a factor of E, it would be the same thing, natural ln of this minus this, right? So the number of blocks is this quantity. So we will show that within each block, the improvement is by a factor of this k alpha by epsilon. Okay. So, sorry, the number of, it's a constant, constant sort of fall, let's say. And the number of steps here is basically to get to this constant fall, right? We will show this is this. The size of each block is here. We'll see this, but that's the idea. Each block gives me a constant fall. How many times? And this constant fall is basically 1 by epsilon, 1 by E factor. So the number of such blocks that there can be should be this ln of this quantity. Phi S0 by phi min is nothing but phi S0 minus phi n. Okay, so this is the idea. Okay, now let's prove the, how much time do I have? Okay, 5 more minutes. Okay, we'll continue tomorrow and then we'll. So the step 1, Sanjay, can you see? Can you all see? If I write on this side of the board?
Camera is yet to be. Yeah, now they have panned the camera. I can see.
The whole thing got garbled. Can you say that again slowly?
Yeah, as you said, the camera was panned, and now I can see what's there on the board.
Okay. 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 All right. So, okay, let's just. So the step 1 would be to show that there exists a player, or what is it? Agent with high cost. Okay, this high cost with respect to the current state of the potential function phi. Okay. This is not exactly. With high cost. This is with respect to current phi. This. Step 2 would be, let me keep some space. I'll write the technical lemma in between them. Step 2. Okay, tell me how do you think I will use this? Like, or rather, what does this actually, does it help in any way? Just having somebody like this. You know, the fan is making all of your words just fly in the air. Okay. So that weeding out can happen if we know that we will never actually enter such a state. Like if I never encounter a state where there are no epsilon improvements. So I'm saying it could be that there exists an epsilon PNE sink there. But I got to, is it possible that I got stuck on a vertex which does now allow me now a path towards one of those sinks? So is it possible that yes, if there exists a vertex where there is no outgoing edge, it means itself it's an epsilon PNE. So in other words, as long as I have a transition out, it means I have not reached a epsilon PNA, right? Now so the point is, if I have a source to sink, if I have a graph which is source to sink, if I don't get stuck on a loop, right? And this is a connected graph. I mean, the thing is that it's not like the sink lies because of the way I have described the graph. So you are saying that it could happen in an arbitrary graph but the point is, if the graph has a cycle, there may not be any source and a sink. Do you see this? A directed graph may not have any source or sink. When is this? When the graph itself is like a cycle, right? It's a when can we say a directed graph will always have a source and a sink? It's a DAG, right? If you don't have a cycle, there has to be a source. If there is a source, must there always be a sink? Yes, that's also possible. But I'm saying like at least a sufficient, when you definitely, if you have this is the thing. So we are avoiding those cycles, right? Okay. So yeah, I'm constantly saying source and sink, source and sink. If I have a source, do I always guarantee to have a sink? Sorry? Yes, exactly. And we use this sort of an idea during the PPAT type of this thing, right? It's that you have a source, then there is a sink. The question is how to find it. Similarly, if you have a sink, you also have a source. So they exist in these pairs. Okay. All right. So the point is there's a source and a sink, there's a path, but I somehow get caught in a cycle. Right? But is that possible? Given that I'm always having a epsilon, is it possible? Because there are only finite number of steps, right? This function phi, this is also something we saw back then. If this improvement for every step is greater than 0, the way the function phi is defined, this is for a finite game. Okay, I should say, I have not said the word finite game. I'm talking about finite potential games, okay? And let's just say finite. There are, in fact, okay? You can have, like we can have infinite games where the possible strategy space itself is infinite. Yes. When we talk about, so no, I wanted to say it because of precision, not because of completeness, that this theorem is for that, not this thing. You're right. The fact that we are having a strict improvement means that we are moving towards, like, wherever we started, we are moving towards a value that on a path that is going to take me towards a minimization thing, right? If I cannot get any lower, it should mean that I have reached the minimum by definition. But I'm saying that kind of, so I'm saying the definition of this potential function, the fact that we can have a potential function that captures the way the costs change for a particular game is what allows me to say that there exists a finite convergence path. Correct? If phi did not do this, then I cannot actually say that. Okay, so, okay, I forgot what was the original question from which we had it. Okay, the point was, how do I use high cost? Just the fact that an agent exists who is paying high cost with respect to what is my current potential value does not necessarily tell me anything. I mean, I don't know how to use it. This agent may or may not have an epsilon deviation right now. Just because he's experiencing a large cost does not mean that he has an epsilon deviation. Right? Okay. So the question is, how do we say that, how do we capture this idea? Okay. I'm not going to say using max gain, but that is this thing. Okay. Max gain allows us to choose, or not allows us, this is the choice. See, these are not I will prove this, but I'm saying if I had this thing, chooses a player whose improvement in is cost of all other players, all players rather, I should say. This is not R, this is K, number of agents. Okay. Suppose I have this. I have this. Max gain chooses a player whose improvement in cost is K alpha by epsilon factor cost of all the other players. Then does that allow me to complete the proof? So the lemma here, think this is maybe this side of what? There exists agent I such that okay. And lemma. It's not clear. Is it clear how this two things give me this? Okay, suppose I had these two properties. Can you now complete this picture is what I'm saying. Chosen by max gain in some step. Important how from outcome S to then can you see the bottom of this board? I have to write this improvement. Yeah. Is greater than. How does? Okay. I will repeat this. Wait. Cj for all j. Yeah. Okay. So this picture, 1 by f e factored improvement, okay? You are at this value phi of S0. S0 is a starting. You apply phi, whatever potential function phi, you get some value. You have to reach this value. We know that the game dynamics is moving as if it's moving via this, right? It's a potential game. There's this potential function. Every unilateral strategy that any player adopts is reflected in the change of potential function. That's the potential game behavior. Keep that in mind, okay? Now I'm breaking this distance phi of S0 to phi min into these blocks. There are several steps, but all I know is after each of these blocks, the fall in value phi of S0 goes from phi of S0 to 1 by E of phi of F0. Next step, it is 1 by E square, 1 by E cube, and so on and so forth. In how many steps am I guaranteed that this, starting from phi of, how many blocks am I guaranteed that I will go from here all the way to phi min? The distance traveled is phi of S0 minus phi of S min, right? Let me write. Each block is basically breaking it down by a factor of 1 by E. So how many such steps you have? So tell me how many factors of 2 like this, how many times can you do? N by 2, n by 4, n by 8, and so on and so forth. Log n times. Same idea is here, except that instead of doing n by 2, n by 3, n by 4, and so on, I'm doing n by E square, n by E to the power 3, and so on. So the number of such steps needed would be natural ln of n. So here, instead of n, I have this value. That's what this quantity is representing. So as long as I can show that there's a block of improvement which gives a fall of this potential function by 1 by E, and I show, then I know that within ln number of phi of S0 minus phi of min. See, ln of phi of S0 by phi of min is nothing but ln of phi of S0. Okay, just take this much about the factor. You will see the details, but that's the idea, that how did this number come about? It's like I'm breaking this into these blocks, and each block has an improvement of 1 by E. Why this improvement is, we will see. But if I could do this, then I would get a bound like this. That's all I said. Okay? All right. So going back to this, all I'm saying here is in every outcome S bar, there exists one agent whose current cost, it meets the average. Imagine, can you have the current potential is phi of S. If every agent had value strictly less than phi of S by K, adding their entire value would give me something that is, adding all their costs would give me a value which is strictly less than phi of S. Right? So this is the averaging argument, right? If all agents had C of I strictly less than phi, this is this thing. Now I know phi of S is what? Cost. This is it, right? At the very beginning. If this is all less than phi of, there are K of this, K times phi of S by K. This is a contradiction. Phi of S is strictly less than phi of S. Cannot happen, right? So there exists at least one agent with high value, which meets the average phi value, correct? Okay. Now, so this is not particularly very complicated. No? Read this. I mean, try to understand this. We are saying in any step, suppose we are at state S bar, and max gain epsilon best response deviation chooses an agent I. Then the improvement in the cost of that agent, this is the improvement, right? It's his cost before deviation, his cost after deviation. The improvement in his cost is at least K alpha by epsilon factor of the cost experienced by all the agents. This is the claim. Yeah, this is the claim. We'll see this. Okay. In particular, note this agent for all agents. These include agents who have no epsilon deviation, as well as agents who may have epsilon deviation. At any state S, I can look at my agent space and say, I can partition it and say, okay, these are the agents who have epsilon deviation and others who don't, right? So this is saying this max gain thing will always capture a agent whose cost, improvement in cost, is at least this much factor of all the other people's cost. Okay, so I will stop here. Of course, I'm going to repeat a lot of this tomorrow because we are past time. But keep this picture in mind, okay? This thing and these two steps. And we'll see how these two things actually lead to my theorem. I mean, of course, we'll prove this. This is easy. I hope you understand this, right? This is just a definition of this. And so this is done. So we'll focus on this and proving the theorem. Okay. Also, we'll start something different tomorrow. So as I said, so as I said, that there are many different ways of thinking about this. This is called best response. It's like, what is the best I can do, best in this case, and my improvement in cost. There exists this notion of minimizing regret, which is a bit like saying, it's not necessarily I'm trying to strictly improve my outcome from where I am, but it's like the loss in my value, I want to minimize that. How best, it's like at the end of the day, I've reached my destination. I'm thinking, oh, I should have really taken the other path. That would have given me a strictly better travel time. That is sort of my regret. Versus sort of I'm on the road and I'm sort of thinking, okay, how can I best improve my, improve my travel? It's that kind of thing, okay? So there are this dynamic, their analysis with respect to minimizing regret and so on and so forth. So yeah, hopefully we'll talk tomorrow, and last week's next class, we'll sort of complete that. And that'll be the end of the